Hey there! As promised, today we're going to dive into three equations with three unknowns. Previously, we looked at systems of linear equations and systems of nonlinear equations where there was two equations, two unknowns, solving for x and y, trying to find ordered pairs that worked in both equations. But today we're going to have three equations with x, y, and z to solve for. So you have three unknowns. So you're trying to find ordered triples that work in all three equations. And so this is a fun process. There's several different techniques you can use, but we're going to focus on one particular technique for this course. Now, before I get too far into the steps here, I want to pull up your textbook for a second. Your textbook at the beginning of the lesson talks a little bit about, the equations and how they'll have three variables, x, y, and z. And when you introduce that third variable, you're now going from 2 dimensions to 3 dimensions. Solving just for x and y, you're solving for ordered pairs. You're looking very two-dimensionally at lines intersecting or other shapes on a two-dimensional flat surface and how they intersect. But as soon as you introduce that third variable, z, you're now looking at 3 dimensions. And so now you're looking at equations that represent planes. If it's a linear equation in x, y, z, you're going to have a plane, and you're trying to figure out, in a system of three linear equations with three unknowns, how do these planes intersect each other? Well, in the pictures there, you can see that three planes might intersect in one single point. Three planes might intersect in a line. Three planes might all be the same location. Or you could have three planes that are parallel, or you could have two that are parallel and only one that intersects both of them. You could have them intersect two at a time, but have kind of almost a pyramid or triangle TP kind of shape. And then you could have two that coincide and then run parallel to a third one. You've got different possibilities. So when we solve, we're either going to find a specific ordered triple, which is like, the one here where you've got the point, or you're looking at, you might have a situation where you've got infinite points. Either the points can lie on the line, or the points can be anywhere on the plane, or you could have no points that they all three have in common. You're looking at for all three, and picture wise, no points in common could be any of these four scenarios, but you're not going to have to worry about which scenario it is. You're just going to have to analytically see, oh, no solution to this. So that's where we're heading. Okay, so let's get down to the steps of doing this. You've got three equations. It makes it easier if we can boil it down to two equations with two unknowns. Boil it down to something you know how to work with. So last lesson we learned how to solve two equations, two unknowns. So that's what we're going to get down to. And we're going to go ahead and use the elimination method to solve two equations, two unknowns. Then once you've got two of the unknowns, you can plug them into one of the equations to get the third unknown. And of course, always take all three x, y, z, and plug them into each of the original equations. Make sure that ordered triple works in all three equations. Okay, so let's get down to the fun of doing one of these. And again, as I said, there are other ways of doing this. One of the methods includes something called matrices, but we're not going to get into that in college algebra. If you're interested in seeing other methods, stick around to pre-calculus, get into some fun there. I especially love matrices. Those are so much fun. But that would be pre-calc. All right, 4x minus 3y plus z equals 9. So there we go, one equation with three variables. So this describes some plane out there in space and its location. And your ordered triples will be points on that plane. Then we have another plane, 3x plus 2y minus 2z equals 4. And then we have a third plane, x minus y plus 3z equals 5. Okay, so here's our three equations with three unknowns. And we're interested in figuring out, if these do indeed intersect, which as we're solving, we'll find out if they intersect or not. And if they do they intersect at infinite points, or do they intersect in one point? Yeah. So that's what we're going to find out. So what we're going to do is we're going to first pick a variable to eliminate. Doing the elimination method. And I'm going to look at this, and they all look like they're equally kind of a little bit of a challenge. Not overly challenging, but none of them jumping out at me right now to be super easy to eliminate. So how about we eliminate z? I mean, you could pick any of them to eliminate. It's totally up to you. Whatever you find easiest, or if you have a vendetta against a particular variable, feel free to eliminate it first. Not sure why anybody would have anything personal against an x, y, or z, but hey. You might want to pick X in case maybe you had a rocky dating relationship. You want to eliminate your ex. I don't know. But anyways, let's eliminate Z. And let me look at the first two equations here. I'm going to take the equations two at a time and eliminate Z. And this is going to produce a new equation with just X and Y. So I'm going to take 4x minus 3y plus Z equals 9. And I'm going to multiply that by 2. And that's going to give me 8x minus 6y plus 2z equals 18. And then I'm going to take that second equation, 3x plus 2y minus 2z equals 4. And I'm going to add these two together. So I'll have 11x minus 4y equals 22. All right. So I need to keep this equation in mind. I don't want to lose track of it. I'm going to need it later. Okay, then I'm going to take personally, you can take any of the ones you just used along with this third one. Probably be easier to use the first equation and the third equation next. So I'm going to take that first equation and I'm going to multiply it by -3. As long as you use one of the two equations you just worked with plus that third new equation you haven't worked with yet. And I'm going to pick this one because all I could do is multiply this by -3, and then that'll be opposite of the +3 there. Whereas if I pick the second one, I'd have to multiply this one by 3 and that one by 2, which is a little more work. You can do that, it's just I was trying to avoid work. Okay, so did that, and then that third equation is x minus y plus 3z equals 5. So I'm going to add those two together. So I got -11x plus 8y equals -22. Okay. So now I'm going to take those two equations and solve. And wow, this is interesting. My x's are already opposite, so I really don't have a whole lot I have to do there. In the interest of space, I'm going to come over here. 11x minus 4y equals 22. -11x plus 8y equals -22. Ooh, interesting. 11x and -11x will be 0x. -4y plus 8y is 4y. 22, -22 is 0. Ooh, so y is 0 in this case. It does happen. 0 is a number, so I didn't do anything wrong. So once I know what y is, then you know what? I'm going to come on up here. And I'm going to take one of those equations that has the two variables, and I'm going to plug in 0 and solve for x. It doesn't matter which one. So let's take 11x minus 4y equals 22. Let's plug in 0 for y. And we find out that x is 2. All right, so far so good. I've got x and y. But remember, the original system has 3 variables. So what you can do now is you can go back to one of the original equations and plug in your x and y and solve for z. I think I'm going to take x minus y plus 3z equals 5. I'm going to plug in 2 for x, 0 for y. 2 minus 0 is 2. Subtract 2 from both sides. 3z equals 3. Z is 1. So there we go. There's my ordered triple. 2, 0, 1. So these three equations I started with are planes that intersect in exactly one point, which was the first picture that that was on that page I showed you a little while ago, on page 424 in the textbook. The single solution picture shows the three planes intersecting at exactly one point. So out there in space at 2, where x is 2, y is 0, and z is 1, there's the place of intersection. If you want to check, you just plug right into the original equations, make sure it works in all of them. Okay, it looks like it works in the first one. Works in the second one. So even if the directions don't tell you you have to check, it's very good practice to check. If I went through and got a math degree, obviously, because I'm teaching you guys math, but if I had never checked anything, I probably would have done at best C's in my math classes. Because you get going and you're working and you make little mistakes and things happen when you're working on problems. But for every math test, I'd get through it and then I'd go back and check every problem. And if I had time, I'd check them twice. And that is what saved me so many times, and I ended up making straight A's. Checking's huge. Even if it doesn't tell you you have to check for credit, it can really save you as far as making sure you're turning in correct answers. So that's my little plug for checking. Anyhow, all right, so there you go. There is the process for solving three equations, three unknowns. Now you're going to find that you don't always get, an ordered triple for your solution. Sometimes these equations, sometimes these planes intersect in different ways. They might intersect or not intersect at all. So let's look at some examples of how to handle those two situations. If they don't intersect at all, you're going to start trying to do your solving just like we were just doing, and you're going to end up with variables disappearing and end up with false statements. And just like when we had two equations, two unknowns, if your variables disappear and you have a false statement, the entire system has no solution. That's one of those cases where the three planes don't all intersect. All right, for example, let's say you have something like 3x minus 2y minus 8z equals 1. That's one of your equations. Then 9x minus 6y minus 24z equals -2. And then x minus y plus z equals 1. All right, I'm going to go ahead and take the first two equations, and all the variables look easy to eliminate, or look about the same, not easy, but about the same as far as eliminating them. So let's say I decide, okay, I do have a vendetta against x, although in real life I don't have any vendettas against any x's because I don't have any x's. I'm one of those weirdos that married my first and only boyfriend. But anyways, okay. Let's take these first two equations. Let's take the first equation and multiply it by -3 so that I can get a -9x. And that'll be opposite of the positive 9x in the second equation. Okay, so there's the first equation. And the second equation, I don't need to do anything. because now my x's in both equations have opposite coefficients. Okay, we add these two results together. Oh my goodness. Upon further inspection, every variable has opposite coefficients. Left side ends up just being 0 because you get 0x, 0y, 0z. Right side, on the other hand, ends up being -5. This is false. Variables are all gone. We end up with a false statement. There is no solution to this. So your three planes do not all intersect at once. Two might intersect, and the third might not, or they might, two at a time might intersect, but all three don't intersect together, like in one place. So in your book, you're just going to see that null set symbol for these kinds of problems and solutions. There's no solution. So there's nothing to check either. You know, this kind of problem saves you time because there's no ordered triples to plug in. Any ordered triple you come up with isn't going to work on all three. If you might find one that works in one of them or in two of them, but you're not going to find an ordered triple that works in all three at the same time. So there's that. Okay, another situation, let's say you have two equations with three variables. You're not going to be able to find, you might not be able to find an ordered triple. Rarely they might be set up where you can, but yeah, no. Typically you're going to be kind of stuck. So what you're going to have to do is pick one of the variables to just be itself. Like let's say you want to solve in terms of z. Then you got to take the other two variables like x and y and get expressions for them in terms of z. And I mean, if you want to pick x, you can get y and z in terms of x, or if you want to pick y, you can get x and z in terms of y, just whatever you want to pick or whatever the directions tell you. And then your ordered triple is going to be expressions that can represent all the ordered triples that will work in those two equations at the same time. And there's going to be infinite possibilities. Because with the two equations, you can't, and if you can't find, without the three equations, it's going to not work for you to find like definite ordered triple numbers. So you got two planes, and the third one's just kind of not out there. Yeah, so you're talking planes, and you might have two planes, and if they do intersect, they're going to intersect in a line, and that's infinite ordered pairs. But you got to figure out, well, where exactly is that line located? And that's what these little expressions help tell you. Okay, so let's do an example of that. Let's say we have the plane represented by 3x minus 2y plus z equals 15. So here's a plane out in space. And we have a second plane, x plus 4y minus z equals 11. You're not going to find an ordered triple because you're not going to have, if two planes do intersect, like imagine two pieces of paper crossing each other, they can't cross each other in only one point out in space. If they do cross each other, it's going to make a line, which it has infinite ordered pairs, but those infinite ordered pairs are specifically where that line is located. So we're going to solve and see if it does have an intersection. If you end up with something that's a contradiction, they may not intersect, they might run parallel to each other. Otherwise, if you find you can work with this, then those ordered triple expressions for x, y, z will help you to be able to find any of the ordered pairs of that intersection, or ordered triples of that intersection. All right, so let's go ahead and solve this in terms of z. So we're going to write the solution set in terms of z. I'm choosing z because that's what the book says to do for this problem. So let's working with x. Let's eliminate the y. We need z in there so we can solve in terms of z. Okay, so to eliminate y, let's take 3x minus 2y plus z equals 15. Let's multiply through by negative 2. And then let's take that second equation, x plus 4y minus z equals 11. Add them together. You're still going to have two unknowns. You have one equation with two unknowns. And what you're going to do, oh, why did I do that? Silly me, sorry. I do not want, I want this to be negative because that's already positive. So I need to multiply by positive 2. Sorry about that. Plus 6x. Some of you are sitting there probably doing this, following along, going, what is she doing? There we go. Okay, so let me erase what I was just doing. There we go. All right, so we got 7x, then the y's will be opposites and cancel. That's the idea, is we're going to get the y's opposites so that the y will go away, we'll eliminate y. And then plus z equals 41. And we want x in terms of z, so we're going to solve for x. So x is going to be 41 minus z divided by 7. All right, so our order triple so far, we have 41 minus z. We can just leave it all over 7 like that. You can just write it as one big fraction. That's fine. We haven't found y yet, and then z is just going to be in terms of z. Okay. So now, whatever z is, you plug it into here, and you'll get your x to go with that z. All right, and then for y, eliminate x. Hopefully I don't goof up on this one. All right, so I've already got a 3 in front of that x, so I need a negative 3 in front of that x. So I'm going to take the second equation and multiply through by negative 3. So I want to eliminate x this time. And this time I've got my sign right. See, as I was saying earlier about checking, mistakes happen to the best of us. It's always good to be checking over your work. I was able to catch my mistake when I went to add these together and saw that the y's weren't opposites. So I could go back and fix it. But it doesn't hurt to constantly be checking over things, making sure it works. Okay, so we got that, and then the first equation was 3x minus 2y plus z equals 15. Add these together, and we end up with negative 14y plus 4z equals negative 18. Okay, I'm going to have to bring this up. I'm running out of space. Carefully draw my little pointer to take it up here. Oh, there we go. All right, so we have negative 14y plus 4z equals negative 18. And we want to solve for y in terms of z. So we're going to subtract z from both sides. And then we're going to divide both sides by negative 14. This will reduce negative 18, negative 4, negative 14. Well, in the numerator, I can factor out a negative 2. And then the denominator, you can also factor out a negative 2. So you can end up with y equals 9 plus 2z all over 7. And that's your y. So there's your ordered triple for that system. Just pick any real number you want for z, and you can plug it into 41 minus z over 7 to get the x, plug it into 9 plus 2z over 7 to get the y, and there's one of the ordered triples that works in those two equations. And there's infinite ordered triples that'll work because there's infinite real numbers you can plug in for z, and then go back and plug in to get x and y. So you get all kinds of ordered triples. And there's no way to write them all, so we express them using these expressions. And then people know, hey, okay, in this case, you're dealing with real numbers. Work it out. All right, next, applications. Yes, so many of these lessons do involve word problems. You do have a handful of word problems that you're responsible for in 6.2. These word problems are going to have 3 unknowns. You're going to carefully label your unknowns with variables. You're going to set up a system of equations using your unknowns. In this case, this lesson, you're going to end up with 3 equations, 3 unknowns. Solve the system, then always check to make sure your answer works. Make sure you've answered the question. All right, let me show for a second and pull up your book. Might be faster just type in the page number. The problem we're going to do is on page 431 in the current textbook. And we're going to be looking at number 44. This is going to be a nice little representation of how to do the word problems. You've got several different kinds of word problems, but the thinking's the same in all of them as far as how to set them up and solve them. A coin collection made up of pennies, nickels, and quarters contains a total of 29 coins. We're looking at number 44. The number of quarters is 8 less than the number of pennies. The total face value of the coins is $1.77. How many of each denomination are there? All right, so how many pennies, how many nickels, how many quarters do we have? And it has to fit the conditions put forth in this question. Okay. Let me see. Since we're dealing with pennies, nickels, and quarters, it's convenient to let P be the number of pennies. I'm not saying the dollar amount, but the number of the actual coins, like if you counted how many pennies are sitting in front of you. Let N be the number of nickels. So again, like if you have 8 nickels sitting in front of you, that is 40 cents, but N would be 8. And Q would be the number of quarters. All right, and it says a coin collection contains a total of 29 coins. So right there we can set up our first equation. However many pennies there are, plus however many nickels there are, plus however many quarters there are, have to add up and equal 29 coins. So here's one of your equations. So that's important to keep in mind. Then it says the number of quarters is 8 less than the number of pennies. You can actually take the words and translate directly to math. Number of quarters, that's our Q, is means equals. 8 less than means you're subtracting 8. Number of pennies is P. So there's your second equation. That equation only has 2 of the variables, but that'll be all right because we are going to have a third equation. Altogether, we have 3 variables. It's going to work out fine. Then it says total face value is $1.77. All right, face value, that's how much they're worth money-wise. Let's say I said, okay, I have 7 quarters sitting here, and I want you to tell me how much they're worth total. Well, since you know that a quarter is worth 25 cents, you would just take that 25 cents times 7 and see what that gives you for the dollar amount. Well, that's what's happening here too, but you've got different coins with different amounts. You don't know how many coins of each type of coin you have. That's what you're trying to find. But you can use that thinking to set up your next equation. Well, however many pennies you have, multiply that by 1 cent each, and that'll tell you the face value for all your pennies. I was trying to kind of move the cursor around that, and I ended up making a mark here. I don't want. All right. Then, however many nickels you have, well, each nickel is 5 cents. So if you multiply 5 cents times the number of nickels, that'll tell you how much the nickels come out to. Each quarter is 25 cents. So if you multiply 25 cents times the number of quarters you have, that'll tell you how much those come out to. Then the dollar amount for pennies, plus the dollar amount for nickels, plus the dollar amount for quarters, has to total $1.77. So there you go. There's your third equation. So let me rewrite the equations kind of together. We've got P plus N plus Q equals 29. We've got Q equals P minus 8. And I'm looking at that and I'm already seeing how this will be perfect for substitution. And then we got 0.01 P plus 0.05 N plus 0.25 Q equals $1.77, 1.77. You know, if it makes you feel better, you can always multiply this whole equation through by 100 and move the decimal point 2 places over on each part. But you don't have to. All right, let's use a little substitution. Let's take this Q equals P minus 8. And let's plug in for Q here. And let's also plug in for Q here. And that'll give us 2 equations, 2 variables. And then we can solve those however we want. If you're allowed your calculator, you can always use graphing. If you're doing it analytically, you can use substitution or elimination. Totally up to you. All right, so we're going to have P plus N plus P minus 8 equals 29, which is going to be 2P plus N equals 37. And then we got 0.01 P plus 0.05 N plus 0.25 times P minus 8 equals 1.77. So let's say 0.25, we distribute right here, it's going to give us plus 0.25 P and minus 2 right there. Okay, so we got 0.26 P plus 0.05 N equals 3.77. All right, so these two, I think I'm going to go ahead and use elimination. I'm going to say, all right, I'm going to multiply 2P plus N equals 37 by 5. So then I get 10P plus 5N 35 equals 185. And then I'm going to multiply that second equation by negative 100. So I'm going to get negative 26P minus 5N equals negative 377. Add them up. I got negative 16p equals negative 291. So p equals 12. All right, so apparently I have 12 pennies. Well, q equals p minus 8. So that's 12 minus 8, which is 4. And then p plus n plus q is 29. So if I've got 12 pennies and 4 quarters, then n must be 13. So that's 12 pennies, 13 nickels, 4 quarters. All right, so 12 plus 13 plus 4 is 29, so that's 29 coins. And if you add them up, you got 12 cents plus, let's see, 5 times 13 is 65 cents plus $1. You add all that up and you get $1.77. So I could check that problem just by going back and making sure everything adds up to the original conditions the problem put forward. The number of coins is 29. Face value for the 3 types of coins is $1.77. So it all worked out. So you can feel confident in that answer and move on to the next problem. All right, so there you go. There's systems of equations, 3 variables, 3 unknowns. I hope you go and practice, go forth, practice, do lots of these. And then when you join us again, we're going to be looking back into 2 variables, but we're going to get into inequalities. So that's going to be really fun too. So we've been working on equations. Usually that's followed by inequalities, and that's the case here too. We're going to look at systems of inequalities in the next lesson. And then finally, the last lesson, we'll get to my favorite, which is circles. So look forward to seeing you. Thank you for joining us. Bye-bye.